Hello and welcome to our lesson on crude oil and fractional distillation. So hydrocarbon fuel or fossil fuels and crude oil all are considered finite, and the reason for that is that in current temperatures and pressures it would take a long time, you're talking millions of years, to make any more. And the word crude is talking about the natural state of the oil when we dig it up. Crude means that it's still in that raw state. We've not yet done anything with it. It's not yet refined. So if you see crude oil, it just means the oil that we've dug up. But the whole point is anything that comes from crude oil, whether it be petrol or diesel or plastics, is considered a finite resource because we cannot make any in a decent time scale. Crude oil itself is pretty useless. We can't really use it for anything, but within that mixture, within the mixtures that are in crude oil are extremely useful products that we call fractions. And you would be expected to know some of these fractions and roughly where they appear on this diagram. So, for example, petrol is nearer the top. Diesel is further down, and bitumen here, that's tarmac, near the bottom. And you need to know that it's fractional distillation that we use to separate these fractions, but just be aware, I have seen questions where they've asked you to write in which fraction it is, and it tends to be the petroleum gas, petrol, naphtha, paraffin sometimes in, sometimes not, diesel, fuel oil, lubricating oil again, sometimes in, sometimes not, and bitumen always at the bottom. So let's go through some of the basics with fractional distillation of the crude oil. So crude oil can be refined and purified, and the hydrocarbon fraction, the different mixtures, can be separated because they have different boiling points. Okay, and this is the key point. The boiling point of these different fractions means that fractional distillation works. If they all have the same boiling point, this would not work. Now, I just want to pause a second, and I want you to remind you that the boiling point is where a liquid becomes a gas. But that temperature, whatever it is, and it's different from different materials, is also the condensing point. It's the point where a gas becomes a liquid. So if I'm heating something up, liquid to gas, you would call it boiling point. But that same temperature is if I'm cooling it down, it becomes gas to liquid. And both of these are important. If you're talking about fractional distillation and you talk about evaporation or boiling, without condensing, you're going to miss out marks. Okay, so in case you didn't know, refined means to be free from impurities. Okay, so let's look in a bit more detail then about why they have different boiling points. So crude oil is a mixture of hydrocarbons, and we looked at hydrocarbons last lesson. So you can see here these kind of displayed formulas of molecules. And each hydrocarbon is useful. Petrol, diesel, lubricating oil, petroleum gases, they're all useful for different things, but together as a mixture, not so much. So let's just look at a few examples. Here's pentane, and you might recognise going, oh, pentane has got 5 carbons. That's got a boiling point of 36. Now I have made up these numbers, so don't worry, but you don't need to memorise them, but it's just there to make a point. Octane, so you might think, oh, oct, so that's 8 carbons, has got a boiling point of 125. And decane, so dec meaning 10, has a boiling point of 174. So hopefully as you're looking at those 3 hydrocarbons, you're recognising that the bigger the molecule is getting, the higher the boiling point. And that makes sense, doesn't it? Because you think boiling points, you think forces, bonds, how much is it going to take to overcome these forces. For hydrocarbons, we're talking about intermolecular forces. We don't break covalent bonds here. We're breaking molecular forces between hydrocarbons. I'm going to come on to that in a second. But hopefully you've recognised that the bigger the molecule, the higher the boiling point. So let's look at the diagram here. I've got a temperature on the left and I've got my mixture on the right. And of course, remembering that the key point to this is going to be the boiling point. So I'm at 30 degrees. they're all still liquids, they're going nowhere. We get to 40 degrees. Now what has happened? Well, hopefully you would recognise that pentane has now gone beyond its boiling point. So pentane would be a gas. Gases go up, off it goes. Okay, and we would keep it at about 40 degrees until all the pentane has been boiled off. Okay, 50 degrees, 100 degrees, 110 degrees, 120 degrees, still all liquids, 130 degrees. Okay, hopefully you recognise octane has now reached above its boiling point, so off it goes again, and you would keep it at that boiling point until all the octane has separated. And we're left with decane at the bottom, or we could continue heating it if we had more. But the point is, the different boiling points are going to be key to making this work. Now you notice I haven't mentioned condensation point yet. We're going to come on to that in a second. So the core concept here then is that crude oil is mainly made of a mixture of hydrocarbons. It does have other impurities in it as well, but you don't need to worry about them. And each fraction, that is groups of hydrocarbons that are similar to each other, so similar lengths, can be separated because it has different boiling points. Okay, so let's go into some detail about fractional distillation. I've chosen 4 hydrocarbons and I've given them some boiling points. These numbers are made up, but they're just hopefully you'll get a really good idea of what's going on. So first of all, you will get marks if you talk about the fractionating column. This is this massive industrial column, several stories high. This is not inside the lab. If you want to look at that fractional distillation in the lab, go back to separation techniques in Unit 2. But this is an industrial scale. This fractionating column is many stories high. It's massive. But it is hotter at the bottom and it's colder at the top. Now, people get that the wrong way around. Don't, because it's an easy mark to get and it's an easy mark to lose. Okay, second of all, before we enter the column, before this crude oil goes into the column, we heat it up. And we heat it up to a temperature where the vast majority of hydrocarbons, all those fractions, are already a gas. So it says here everything vaporizes. The word vaporizes means it becomes a gas. So you might see that word in an exam question. Don't fear it. It just means it's turned into a gas. You might say evaporation, you might say boiling, you might say vaporizes. Any of those words are absolutely fine. Okay, so each of our hydrocarbons, they've gone into the column now. And let's put some numbers on here. Now, again, I've made up these numbers just to make a point. If the exam questions give you different numbers, just use the ones in front of you. That's absolutely fine. Now you'll notice first of all, the green dot, my green hydrocarbon, is actually at 250 degrees there. It's actually still a liquid. It hasn't boiled, it hasn't vaporized. And so some of the really hard, so the really long chains with really high boiling points actually come into the column as liquids still. And all that will happen is that they just kind of drain off the bottom as a sticky tar-like substance. And this is what's called bitumen, and it's the stuff that we use for putting on the road. So this is literally tarmac, but the proper name for tarmac is bitumen. Okay, so then let's look at the red hydrocarbon. Now the red hydrocarbon has a boiling point of 200 degrees. So at the moment where it is now, it's a gas, and so it's going to rise upwards. And it can't quite get past this point because up here it's 100 degrees. Here we're just getting to about 200 degrees. And so it kind of stops about here. Now the thing with gas is it can get through these little chambers here, because obviously gases can get everywhere. But as a liquid it can no longer go any further up because liquids don't travel up, and so it will filter off down through this pipe and it will end up coming out here as a fraction, and that might be something like, I don't know, diesel oil or something like that. Okay, let's look at the yellow hydrocarbon. Now the yellow hydrocarbon would be travelling up alongside the red. As the red stops, the yellow continues because it's got a lower boiling point, and it's still a gas. It's still a gas when the red becomes a liquid. It keeps on going, but it gets stuck here. Why? Well, it can't go any further because it's getting too cold. It's turned into a liquid. It's condensed. That's where this condensation comes in here, the condensing point. And so it's a liquid and it travels out this pipe here and it would come out these separate pipes, and we'd have something like this, and that might be something like petrol. Okay, so what about the blue one then? Well, the blue is a gas as it goes in. It's going to travel up with the red. It's going to go past the red, past the yellow, and actually, even at the top there at 30 degrees, it remains a gas. So some of them still come out as a gas at the very top, and this is the sort of fraction that you're going to be using in cooking and heating your homes. So what are the main points here? You've got to talk about evaporation and you've got to talk about condensation. And the point is that they condense, they're evaporated, they travel up the column and they condense at different levels, and therefore they are separated. So the fractions condense at different levels because they have different boiling points. Remembering, of course, that number, whatever that boiling point is also the point it condenses. It turns back into a liquid. That is the temperature turns back into a liquid if it's getting colder. So the question then is, well, why is it that the shorter chains, the smaller molecules, have lower boiling points? And why is it the longer chains or the big molecules have higher boiling points? Well, you should know that boiling point is to do with the energy needed to break bonds or to break forces. So in this, and you've got to be careful with your wording, you're not talking about breaking the covalent bonds, okay? These are the covalent bonds, those lines, and covalent bonds are strong, okay? We are not breaking the bonds. If we were breaking the covalent bonds, we would end up with carbon and hydrogen, and we're not. We are ending up with methane, ethane, propane, whatever. So we are breaking the intermolecular forces. This one here, where's my pen? Where's my highlighter? My intermolecular forces. This is what we're talking about here. And because these particles, sorry, not particles, because the molecules are small, there are fewer intermolecular forces between these chains. So between this molecule and this molecule, there is an attraction, there is an intermolecular force, but it's not very strong. So it's not going to take a lot of energy to break it, and that's why they have low boiling points. Whereas you can imagine, because this molecule here is much bigger, these molecules are much bigger, the attraction between these molecules is going to be much stronger. They have more intermolecular forces, or they have stronger, it's usually more, to be honest with you, more intermolecular forces between these two chains here, and therefore it's going to take a lot more energy to break that force, to overcome that force, and to boil it. So short chains, low boiling points, few intermolecular forces. Long chains, high boiling points, more intermolecular forces, and it's molecular forces, not bonding.